Previously, when I was talking about improper integrals, I pointed out that it wasn't enough for a function to come down to 0 like this for the integral to be convergent. It had to come down to the x-axis fast enough. And I had mentioned that the borderline case was 1 over x when it came to these reciprocal power functions. And I want to just give this as a fact. The book doesn't have it as a theorem, but we'll treat it as such because what we want to look at coming up is determining whether an integral converges or diverges by comparing it to something that we do know. And this is typically what we're going to compare with. And so we want to just look at this for a second and make sure we understand why it's true. If we just go through the integration briefly, we can see why there's a distinct difference between those cases. And I'll leave p equals 1 out of it because we did that, right? We actually integrated 1 over x to the 1. And we saw that if you were starting past that vertical asymptote, the integral from there to infinity was divergent. That's why this is starting at a greater than 0. Remember, these guys all have a vertical asymptote at 0. So we're assuming we're already past that. So if you're somewhere past that vertical asymptote and then you integrate out to infinity, that's what we're looking at. So let's just see in general what happens with that integral. So that integral, remember, first we have to make it proper. So I'll say as b goes to infinity, the integral from some positive a up to b of 1 over x to the p dx. And then assuming that p is not 1, if p is 1, that's kind of a special case, right? Because then that's natural log. But if p is anything else but 1, that's just power rule. So it's probably best to think of that as x to the negative p. So from power rule, you raise that by 1. So that's x to the negative p plus 1 over that exponent. So I'm just doing power rule there. And then we're going to go from some positive a up to b. b into there. Minus a into there. OK. And so we have something like that. Now this part really has nothing to do with convergence or divergence. Remember, a is just some number. We could be starting at 1 or 2 or 15. So this is, regardless of p, that's just a constant. What matters is what's happening as b goes to infinity here. And notice what could happen with this exponent if, say, p is greater than 1. Well, I'm going to subtract that p to the other side. Then that exponent, negative p plus 1, is actually a negative exponent. So that quantity is really on the bottom of the fraction, right? So you have b raised to some power that's really negative. So it's b to that opposite power on the bottom there. So as b goes to infinity, since that's really on the bottom of a fraction, that's going to go to 0. So let me write it that way just to make it clearer. If I move that to the bottom, the exponent's the opposite, right? So I have that negative p plus 1, which is just some constant. And then I've got b to the p minus 1. And so as that grows, this is heading to 0. But for p less than 1, again, add that to the other side, or subtract it from both sides. I have that. In this case, when p is less than 1, that exponent is actually positive. So that really is on the top of a fraction. So you got a number that's going to infinity raised to some power there on top. And we know that goes to infinity. So B. Now, because this didn't matter, this was just some constant. If p is greater than 1, we see that that's going to head to 0, and we're just going to have that constant. So we're going to end up being convergent over here. But over here, that's going to take off to infinity, and this is going to be divergent. And that really is the difference. And then, as we saw, when p is 1, it's divergent. We already did that integral. So for now on, we're going to assume this as a fact. So when we go to compare integrals here in a little bit, when we do our direct comparison and limit comparison tests, the thing that we're going to try and compare with is stuff of this form. Because now, all I'm going to argue is that that thing is convergent or divergent based purely on that exponent. I'm not going to actually do the integration anymore. I'm just going to know that things like this converge if that exponent's greater than 1, and they diverge if it's less than or equal to 1.